very briefly. So I posted a study guide under the course content folder, study guides. I put a study guide up for the test, and I told you the content is chapters 11 and 13. They're going to be the test on Thursday. And I put a note at the bottom about the questions on the old exams. This is the first year we started on chapter 11. So if you'll go back and look at the previous 3 times that I've taught this course, which were 17, 16, and 14, the materials we covered those years, exam 1 was over chapters 10 and 11. So 10 is not going to be on the test at all. Okay, so you're really going to have to look at the back half of, or the last set of questions on the multiple choice on exam 1 and the first chapter on exam 2 to see material that's equivalent to ours. So you're just going to have to, this is with the change we made this year, you're going to have to stagger or look at multiple tests if you want to see those types of questions. Again, questions are places that I think encourage you to do in your study habits is certainly review your Mastering Chemistry. At the start of every chapter, I gave you some suggested problems. Some of them are repetitive. Those are some of the problems that we'll do in class. That we do the parallel exercises at the end of the class. We'll work through some of those again tomorrow. If you have any old test questions tomorrow, it'll be a good opportunity. If you have any at this point, we can review some of those. So I'll give you all a choice here. Would y'all rather, we're going to work the problems at the end of the chapter so you can finish up the Mastering Chemistry that's due on Wednesday, so the chapter 13. Would y'all rather work old exam questions? Would you rather that on Tuesday, after we go through the problems at the end of the chapter, finish up the notes so we can spend all day Wednesday reviewing? Or would you rather ask questions on Tuesday afternoon and we go over material that's going to be on the test on Wednesday? Does it matter? Which one's over there?
We do Wednesday.
Say again?
Yeah.
Okay, so I don't think we're going to like 15 slides maybe 20. We'll finish it. It won't take that long. We won't spend the entire time period on Tuesday then. And then we'll spend Wednesday doing all day Wednesday for review. Okay? So that means that y'all need to bring me your old questions, okay, or questions that you have. We'll pull up old exams. So I can pull up any old exam that y'all have listed, and we can work through those problems together. Same the questions at the end of the chapter. If you got questions, let's take a look at them then. Okay? All right, so that's what we'll do then. So we will probably then tomorrow finish the notes first. That way when we do the end of chapter problems, we can go over the whole chapter. Okay. All right. So concentrations is where we are. So we're talking about different ways to express concentration. We did a couple of clicker questions on them. We're kind of mixed. Some of you did very well on them. Some of us have got some room for improvement. One of the other ways that we express concentration is in the parts per. Now, the common way that we express parts per is typically parts per 100. That's a percentage. But there are some other ways that we express it as well, especially when you start looking at lower concentrations. And when you describe parts per, it could be in describing it mass, or it could be volume, and rarely do we have the combination of mass volume, but occasionally that's a set of units that we have as well. Typically what we have are the units are going to be the same, so if it's mass, it's grams over grams. If it's volume, it's milliliters over milliliters. The confusion comes when you have something like grams per milliliter, but again, as long as the units are defined, it'll work out. So if we look at mass, anything that we're going to describe in mass could be any combination of units, grams over grams, kilograms over kilograms. It would even work for pounds over pounds, even though pounds are really not mass. That's a measure of weight, which is a force. So, but it would still work in the ratio because the acceleration due to gravity is constant and it would cancel out. The same is true in volume. Milliliters over milliliters, liters over liters, gallons, doesn't matter as long as they cancel out top and bottom. So you can put any kind of combination there as long as you specify exactly what those are. It's important in a percentage that you write the units after it that you expect. So part per 100 is our common one that we have. So I'll try to hide that back there. So part per 100 means that there's 1 in 100, and where that's useful for us when we go to try to do dimensional analysis or factor analysis and solve the problem. If we say a solution has 0.9% by mass, that means that there are 0.9 grams of the solute for every 100 grams of solution. So that would be the way that I would write that up in the dimensional analysis problem to solve something with that. I'd say that there are 0.9 grams of the solute over 100 grams of the solution, and now that's my expression of concentration. I can convert it to whatever I need to. But think of in something of percent, anything that's percent, you're going to represent it as that per 100. If it's mass, 100 mils. If it's volume, it's 100 milliliters. Right. Now, a smaller representation to represent lower concentrations that's commonly used is the term part per million, and we represent that ppm, and it simply means 1 part in a million parts of solution. So if I say something is 36 parts per million by volume, that means that there are 36 milliliters of the solute per 1 milliliters or 1 million milliliters of solution. And that's a large volume of solution if we want to think about that in terms of what an equivalent to that is. All right, so if I think about what is a million milliliters, so that's going to be equivalent, convert it to liters. Right, so that's 1,000 liters of solution. You're talking about a volume of solution that's approaching the size of this room. That's nothing we're ever going to use in the lab at a volume that size. But when we have a solution that's very, very low in concentration, we may represent it in something smaller. So a way that we would convert this is something like 36 microliters per liter would be a part per million, where micro term represents 10 to the minus sixth. And frequently we make up solutions that are that dilute, okay, that are concentrations that low. There are a lot of things that are things of environmental concern. So there's human exposure, animal exposure, aquatic exposure, that at the part per million level that they're toxic. And that's something we have to be aware of. So when we think about parts per million, we can think of it in terms of grams of solute per 1 million grams of the solution. And if we want to convert the units around, make numbers a little smaller, it's still a 1 to 1 million ratio. It's 1 milligram of solute to 1 kilogram of solution. And if it's an aqueous-based solution, so if the density of water is equal to 1, so if it's aqueous-based in water and the density of water is equal to 1 exactly, what happens is a liter is equivalent to a kilogram. So when this happens, if it is aqueous-based, it becomes a milligram of solute per a liter of water. Now, we have to think about milligram. It's 3 decimal places. Okay? Our balance down in the lab only reads to 3 decimal places. So when we try to measure something, we can't even measure this accurately with the balances that we have. It's still a very, very, very small quantity. Usually when we describe things in aqueous solutions, we'll use the approximation that a kilogram is approximately equal to a liter of water if it's aqueous. Because the density doesn't change much for dilute solutions between that and pure water. So we can get away with this conversion. We can use this conversion to say that a part per million is a milligram of solute per liter of water. But if we want to do it in true mass, we simply take the mass of the solute divided by mass of the solution, and a part per million means we multiply it by 1 million. Same as a percent, you would multiply it by 100. My mouth's really dry. drinking water. Too many decongestants. All right. There's a lower concentration we use, and there are a lot of things that, especially things that are carcinogen or extremely toxic to the environment, poisons, things like arsenic-based pesticides. We're concerned even at lower concentrations. To express those concentrations, we use the term part per billion. Works the same, exactly the same. It's the mass of the solute divided by the mass of the solution times now 10 to the 9. 1 part in 1 billion. If we wanted to write the equivalent in an aqueous solution, a part per billion is equal to a microgram of solute per a liter of solution if it's aqueous base. So water-based solution. Now, microgram represents 10 to the minus 6. We have one balance in the whole department that can weigh out a microgram, and it's a $35,000 balance. And only the students that do research projects ever get to touch that. 35 grand. All right. Very, very difficult to weigh out that amount. Things like static electricity. If you've got static electricity on your clothes, you have to run through your hand through a high voltage deionizer to wipe the static charge off your hands. Otherwise, you transfer enough static charge onto a plastic container that'll throw the weight off 30-40% when you try to measure micrograms. Extremely, extremely difficult to do. So there are some things at these low concentrations we have to be aware of. A lot of the things that are extremely toxic for us, we're concerned about them being present even at part per billion levels. And I give you a couple of mastering chemistry problems to look at these. If you go on and do a chemistry major and take chemical analysis, we'll learn all about those. But parts per millions and parts per billion are used all the time in environmental concerns and expressions. So when you report to Farmer Bob, okay, what the level of a toxin is in the pond water his cows are using, they're not going to use molar concentration. They're going to use a part per a million or part per billion, because everybody pretty much understands percent, part per 100. You start learning that in middle school. You just convert it to 10 to the minus 6 or 10 to the 9, and you've got in parts per million, part per billion. It's a easier concept. All right, so the next term that we want to learn to express concentration is the term called a mole fraction. And we've used mole fractions already a little bit. We use them in the ideal gas law chapter. But a mole fraction is simply the fraction of moles of a component that you're interested in over the total moles of all the components that are in the solution. And if we think of a mole fraction, the fraction is describing the piece that represents that solute, and all of the pieces have to equal the whole. So the summation of all the mole fractions have to equal up to 1. And if we describe mole fraction as a percentage, it's simply that mole fraction multiplied by 100 to get a percent number. Now, mole fractions are unitless, and if we look at the value way that we describe it, it's the Greek letter chi, so it's a weird looking little X. And if we think of the solute versus the solution, the pieces have to equal the whole. So if there's only two things, solute and solution, those two mole fractions have to add up to exactly 1. All right. If there are multiple solutes in it, all the pieces plus the solution have to add up to 1. In the same way, if we think about this in terms of the percentage, okay, the summation, okay, this means add all the pieces together of all the mole fractions, or however many components are there, would have to add up to 100% when we're talking about percentage, versus adding up with 1 when we're talking about mole fractions themselves. Okay, so kind of an approach to look at when we're doing this. One of the things that you want to do is think of concentrations as simply a ratio. It's an amount over another amount. whether it's moles over liters, grams over grams, whatever that is. So we can separate that ratio into the numerator and denominator terms. Okay, so we want to put the solute on top, the solution on the bottom of it. Now, in some cases, like we talked about molality, we're just going to put the solvent on bottom. But everything else uses the solution on bottom. And then the next thing we want to do is start using dimensional analysis and take the solute part to get it into the unit we want. Do we have grams and we need to get it into moles? Or is it grams of one material and we need to use the stoichiometry of a reaction to go from grams to moles, moles of compound A to moles of product C? Okay, what do we need to do? Just set up the dimensional analysis, see that things cancel out. That's your key to make sure it works. So convert the solution into the required units that you need. Your units match, and think about the definitions that were talked about to define the new concentration units. And again, always set up the dimensional analysis. If your units don't cancel out with what you want on top and bottom, okay, something like grams over liters, then you don't have the problem set up right. So this is some of the common assumptions that we can do just to simplify our calculations, or gives us starting points more than anything. If something is percent mass, I assume that it's so many grams, whatever that percent is, per 100 grams of solution. Okay, so I showed an example of this a while ago, but I want to just clarify it. If I say something is 11.33 percent mass, if I want to do that in dimensional analysis, I would say it's 11.3 grams of the solute per 100 grams of the solution. So that would be an equivalent in terms of what the percent means on it. If it's mass volume, again, you would assume that it's 100 mils volume, so many grams of the solute per 100 mils of solution. If it's part per million, it's the number of grams of the solute per million grams of solution. If it's molarity, it's going to be the number of moles per liter. So if we think about molarity and the units that we're going to use with molarity, it's moles per liter. So we usually describe this in terms of 1 liter of solution. If it's molality, so with molality, now we're talking about just the solvent. So we describe the number of moles per kilogram of solvent. And when we talk about if we have a given amount of a substance, assume you use the ratio if you've got 1 mole of that solute per solution. And we're going to look at examples of this. All right, so sometimes your given amount of solution, you need to determine the amount of solution and the units are not given to you and what you need to search for. If you assume the amount of solutions in grams, you can use density to convert that into volume and then to liters if needed. So the relationship that's going to go between mass and volume is going to be density. If we have an amount of volume, we can use density to go to grams if needed. If we think about determining the amount of a solute that's in a solution, we can take that and describe it in terms of mass or moles. If I ask you a question like this, I'm going to specify on the test, what is the amount of, and then I'm going to say in grams or moles in parentheses behind that, of whatever the solute is in a certain volume and concentration of the solution. If I fail to do that, either answer you give me would be correct, because it describes the same amount of that material, whether it's in grams or moles, but I'm going to specify what it is. Sometimes we need to know how much solvent's needed to get to a certain concentration. We describe the amount of solute. It could be in terms of grams or in moles, or more commonly describe it is in volume. Yeah, right. Marker. Or volume. The key thing is look at the definitions for what the units are, set the dimensional analysis up so things cancel out. And again, this is the same table that we went over earlier. This is the table 13.5. And if you'll go look at the study guide that I put up for you, this table's on the equation sheet. So you're going to get this table to use with the test. So use this to work your problems in the Mastering Chemistry and review as you do the old test problems, because you're going to get this exactly. All right, so it tells you the relationships. It also tells you the units associated with these different expressions of concentrations. If you don't have those units at the end of your calculation, everything else cancels out. You're not getting the right answer out of the problem. All right, your units and your dimensional analysis tell you you've done things right. Some people like flowcharts. So this is a flowchart that shows the relationship in these things. And don't try to copy all this down. You can go get it. It's in the notes. And print this out as a single page if you want to. So you may want to do that. So take this guy and print full-size single page. All right. It's in your textbook as well if you've got the text or the e-text. You can take a look at this. But it gives you your relationships to do your conversions with all the different expressions. So you can think about your solute and your solvent and how you go from the amount of a substance to mass, your relationship's molar mass. How do you go from the amount of moles to a volume? It's the molar volume of a gas. To go from mass to volume, the relationship is density. And you can do a similar thing when you talk about the solvent. So if I need to know the molality of something, it tells me I need to know the amount of the substance in moles and the mass of the solvent. And I'm going to have to convert from grams to kilograms. It just tells you the relationships. Some people really like flowcharts, and it facilitates the way that your brain's wired to learn. Some people can look at a table and get the same piece of information. And there's really those two tables, this table and this flowchart express the same information. It's just which ways it work for you better. And that's the thing that we want to figure out. Okay, so I'm going to work a couple of different problems here to just look at examples. And we're going to use this same data set with several different problems. All right, so we'll kind of get used to this guy. So on the this particular problem, it says what is the molarity? So molarity is capital M, and it's going to mean moles of the solute per the liters of solution. That's where I'm going to try to get to. What's the molarity prepared by mixing a certain mass of C2H6O2, that give you its molar mass, with a certain mass of the solvent, and it makes a total volume of solution of 515 milliliters. Okay, so if I want to calculate molarity, I'm going to start with the mass. So I've got 17.2 grams of the solute. And I need to go from mass. I'm trying to get to moles, find out how many moles are on top. And the relationship between mass and moles is the molar mass. So to convert from grams to moles, I'm going to put the molar mass of this compound on bottom. All right, so I've got the number of grams per mole. So now I've got this on top where I need it. Now I've got to look at the solution. So this is per this 0.5 kilograms of solvent, but that tells me how much solvent is. I need to know how much solution's there, and I need it in liters. Well, what I've got is 515 milliliters is the amount of solution. So all I need to do is do a conversion from milliliters to liters. Before I even pick the calculator up, I'm going to make sure my units cancel out. So milliliters of solution, top and bottom cancel out. The grams of solute, top and bottom cancel out. I'm left with the moles of the solute per liters of solution. That's what I'm looking for, so I've got the problem set up right. It's just a matter of ranking through the calculations. All right, so let's do that. So I've got 17.2 times 1,000 divided by 6207 divided by 515. That seems pretty small. I'm going to try that. I'm going to double check my calculation. It's smaller than I expected to see. Yeah, I didn't get that the second time. I'll leave this number more. Anybody get that? Okay, I like that better. So I entered something in wrong in the calculator. Hey, question on that one.
What did you multiply 17.2 by?
Okay, so everything on top.
Oh, with the open house.
So everything on top was multiplied together. So I took this times the 1 times 1,000, and I divided by everything on the bottom. And that would have been a 1 in that one. Okay. Anything else? Okay, so now we're going to take the problem and we're going to change it just a little bit. The same solute, 17.2 grams, same molar mass, the same amount of the solvent to make the total volume. The key word is what am I looking for? Now I want to know what is the molality. Okay, so I'm going to work through the problem the same way. I want to try to get the units to get molality, and molality, small m, is the moles of solute per kilogram of solvent, not solution, solvent. So this one's going to be a little different. Okay, start with what you know. So first thing I want to do is I want to find out how many moles of the solute do I have. 17.2 grams of solute. It weighs 62.07 grams per mole of C2H6O2. Okay, so halfway there. Only thing I need to do now is put kilograms of solvent on bottom. And in this particular problem, it tells me exactly the kilograms of the solvent, which is water in this case. So if I just look at my units, grams and grams have canceled out. I've got moles of the solute over kilograms of solvent. This one's even easier to do. And usually when you write a concentration, you express of what? Okay, so here this tells me what my solute is. Let's put that chemical formula behind it. So I got 0.554. Molal is how you would say that one. Okay, question on that one. All right. Same set of data. Now I want to know what is the resulting percent by mass of this solution. All right, so I want to know what is the percent by mass. So that means I need to have the grams of the solute over the grams of the solution times 100 to get it in a percent. Okay, now we've got all that data there, so I take my 17.2 grams of the solute, divide by the mass of the solution. How much solution do I have? Okay, so I've got 500 grams of solution. What does the solution include? Is it just the solvent? It's the solvent and the solute. So it's 500 grams of solvent plus the 17.2 grams of the solute. So the solution weighs 517.2. Okay, now times 100 to get it as a percentage. And I get 3.33%. And I need to specify the units of it. Mass. That tells you the volume, and if it were mass volume, that would be the one we use, but this one's mass. Good question. What else? And the thing I'll encourage you to do, you just got to practice some of these things. Same set of data. Now we want to know the mole fraction. All right, so I want to know the mole fraction. What is the chi of this solute, C2H6O2? What I need are the moles of the solute divided by the moles total. Okay, so we've talked about how to find the moles of the solute. So let's just start setting the problem up. So the moles of solute is the 17.2 grams of C2H6O2, and convert it from grams to mole using the molar mass. Write the number down right. Grams C2H6O2 per 1 mole. And now we need to do the same thing on the bottom. I need to know how many moles there are of solution. So it's the moles of the solute, which is just going to repeat this. So this is going to give me the moles of the solute plus the moles of the solution. So if I want to know, or the moles of the solvent, so if I want to know how much of the solvent I've got, I'm going to convert this kilograms into grams. So we've already said that's 500 grams. And then I need to take the molar mass of water, since this solvent's water. Water weighs 18.02 grams of water per mole of water. And if I just look at my units, what do I have? What's left? Grams and grams of the solute cancel out. I'm left with moles on the top. That's what I want. All right, on bottom, grams and grams cancel out. It gives me moles of the solute. Grams of water cancel out. It gives me moles of the solvent. So those two are going to add together to give me my mole total. Okay? And what's the range of values that chi can be? Between, what's the numbers it could possibly be? Between what and what? 0 and 1. None of it 0. All of it 1. So I'm always looking for a number between 0 and 1 when I do a mole fraction calculation. It's just a check I can do to see if I've got it done right. All right, so 17. I got an error. got a pretty small number. Hopefully somebody else got this. Anybody else get that? 00979. I may have entered the number wrong then. Yep, I got y'all's number this time. I think I entered it as 18.2 instead of 02. Okay, so that gives me the mole fraction for the solute. So this is my chi of the solute. What if I wanted to know what chi of the solvent was? What would be the easy way to find that? So if I wanted to know what is the mole fraction of the water? Okay, I could just put the water on top. That'd be one way to do it. But I know the pieces have to equal the whole. So the shortcut is just subtract from 1. Put 99 and round to 0 to 3 significant figures. Okay. Or you could put this term on top instead of this term, and it would give you the same thing. Question on mole fraction. Okay, so now we're going to make percent mole fraction. Well, I'm going to simplify this one a little bit. I'm going to go back and take our number from the previous page. Once we found the mole fraction, all we need to do is multiply it by 100. So our mole fraction was 0.00989. So chi of C2H6O2 was equal to 0.00989. And if I want to convert that to the percent mole fraction, all I do is multiply it by 100 to get it a percent. So percent mole fraction. So all I need to do is move the decimal place to the right 2 places. And I've got the mole fraction in a percent. In a similar way, if I wanted to know what was the percent mole fraction for the water, I would take 100 less the solute, which is 0.989, and I'd get 99.0%. Okay. Well, guess what? Still got another example. I thought it was y'all's turn. Okay, so I'm trying to do as many examples as I can pull out here. So I want to make a solution, and I'm going to take 35 grams of ammonia and put it in 90 grams of water, and it tells me the density of the resulting solution, and I want to know what the molarity of the ammonia, the NH3, is. So that means I need to know the molarity of the ammonia, the NH3, is going to be the moles of ammonia over liters of solutions. So that's where I need to get to on my units. All right. So when you set this up, you're going to set it up with what you know is going to be on top. All right. So I've got 35 grams of ammonia. Ammonia has a molar mass of, we're going to have to add it up. It's not given in the problem. So Ammonia or nitrogen is 1401. Each one of the hydrogens, it's around 1703, I think. 3, 1, yep. So it weighs 17.03 grams of ammonia, NH3, per a mole of NH3. All right, so now I've got the top part of what I'm looking for. I got to find this volume of solution. Okay, so what I know is the grams of ammonia, and I know the grams of water. But I need to know what is the volume of solution. How do you think we might find that? So do I know the total mass of the solution?
Yes.
What is it? Yeah, so I know the total mass of the solution is the summation of the 35 grams of ammonia plus the 90 grams of water. Okay, so if I add those together, I get 125 grams of solution. But now I can use the mass of the solution and the conversion factor between mass of something and the volume of something is density. Okay, so now if I use density, it's the density of the solutions given. So 1 milliliter of solution has a mass of 0.898 grams of solution. Okay, that's going to cancel out grams of solution, and I'm in milliliters, but really to solve this problem, I need liters on the bottom, so I'm going to go ahead and do that step here. There are 10 to the third milliliters per 1 liter of solution. Milliliters and milliliters cancel out. I'm left with liters. That's what I want. So I'm going to do the math on this guy. So 125 divided by 0.989 divided by 1,000. That's equal to 0.139 liters of solution. 0.139 liters of solution. I'm going to check all my units. The grams and grams of ammonia have canceled out. I'm left with grams of ammonia and H3 on top. Liters of solution on bottom. That's what I want. So I'm there. So 35 divided by 17.3. This is actually a pretty concentrated solution. This is about as concentrated as you can make if you try to saturate. That solution is 14.8 molar ammonia. The trick on this problem is recognizing you have to add both of these masses together because they compose the solution. And the density represents the solution. You gotta get the total mass. Okay? Question on that one? I swear I got a bunch of problems coming up for y'all in a second. Nope. Here we go. All right. One of these days. All right. So what is the molality of a 4 molar solution? It's 4.0 molar sodium hydroxide, and I've got the density of solution. All right. Another example. So I've got 1 unit of concentration. I've got to go to another. So I'm looking for molality. So that's going to be moles of the solute, which is sodium hydroxide, per kilograms of the solvent, which is, I'm going to assume here is water because it doesn't tell me anything else. All right. and the density matches that of water closely. Okay, so I know in this particular solution, I have 4 moles of sodium hydroxide per a liter of solution. Okay, but what I've got to do now is convert this liters of solution into kilograms of solvent. So let's figure out how to do that. So what are your ideas? Okay, let's use the density and go from 1 liter to milliliters, 10 to the third milliliters. All right, and now I'm going to use the density. So I've got, in this 1 liter, I've got, the density is 1.04 grams of solution per 1 milliliter of solution. Okay, now that gets me closer. Liters and liters cancel out. Milliliters of solution, milliliters cancel out. I've got moles per grams of solution. What's the problem with what I have? Kilograms of what, though? Solvent. And I've got solution. So what I've got to do is I've got to figure out how much of this solution is solvent and how much solution is solute. And this is kind of the tricky part to this particular problem. So what I'm going to do is assume I have 1 liter of solution. All right, so I'm going to do a little side step here. And I'm going to assume I have 1 liter. So if I've got 1 liter of solution, and if I took the density of it, so if I had 1 liter, which is 1,000 milliliters of solution, and I use the density would be 1.04 grams per milliliter of solution. So that means that has a mass of 1,040 grams of solution. Now I know the solution is equal to the mass of the solvent plus the mass of the solute. So what I need to do is find out how much is the solute that's in there. Well, I know in that 1 liter, it's equivalent to 4 moles. So what does 4 moles of sodium hydroxide weigh? So what I'm going to do is take 4 moles of NaOH. I've got to calculate its molar mass, so it's around 40. So it's 22. There it went. 22.99 plus 1.08 plus 16. Yeah, it is 40 exactly. So 40. Oops. It needs to be on top. It weighs 40.00 grams per mole. So that means I've got 160 grams of sodium hydroxide in this solution. So of this solution, if I subtract out the 160 grams of sodium hydroxide, what I'm going to be left with is the amount of water that's there, which is the solvent. So that means there's 880 grams of water in that solution. Okay. So now I take that 880 grams of water and put it in terms of kilograms. All right, the units I have left are moles of the solute per kilograms of solvent, and that was hard to come up with, but that's where we are. So 4 divided by 1,000 divided by 1.44, divided by 0.880. That ain't right. So I came up with a number that's really small. 0.004. Okay. What did I set up wrong? Moles per liter of solution, that's right. Okay. You need to get rid of the 1,000 term in here. So, if I think about this, a liter of solution, I did the math down here instead of up here. I tried to put it in the problem twice. So, let me go back to my eraser. All right, so 1 liter of solution, this is what we found out here. We had 1 liter of solution. We found that it had that much water in it. So all we need to do is divide it by so now liters of solution cancel out. Now I've got kilograms on bottom. Tried to do 2 pieces of the problem twice. That's a much better number. And this I'll use sodium hydroxide. How do I know what?
How did you know it was wrong the first answer?
I knew it was wrong because I came up with 0.0003, something like that. And molality and molarity are going to be somewhat close to each other if density is near 1. So I was expecting a number a little bit greater than 4. And it was messed up. So that's just one of the things you kind of get from experience. But the other thing I should have looked at to saw, I did these conversions using density. I was trying to do it twice in the problem. And that's where I was dividing it by 1,000 too many times. Okay. Golly, I hope you are next. Nope. More me. Okay. Okay, so we're going to make a solution where we're going to take 63 grams or 76.3 grams of sodium iodide, give you a smaller mass. I'm going to put it in a certain volume of water. And I want to know the mole fraction if the final volume is the certain amounts. Okay, so what I'm looking for is mole fraction. All right, so to solve for mole fraction, and these are all old test questions, I need to know, so chi of the sodium iodide is going to equal to the moles of the sodium iodide divided by the moles total. So the solute plus the solvent. And I wrote mass instead of moles. Moles total. Okay, so we know how to calculate moles. We've got 73.6 grams of sodium iodide. It has a molar mass of 149.89 grams per mole of sodium iodide. So what's on top? The grams cancel out. I'm left with moles. That's what I want. Now I've got to look at the total. So now to find that, it's going to be the moles of the sodium iodide plus the moles of water. Okay, so find the moles of sodium iodide. I'm going to repeat what I just did. On bottom. And if you want to break this up into different steps, that's fine. Now I'm going to take the mass of the water. Looking on the bottom, grams and grams cancel out. Grams of water cancel out. So I've got moles on the bottom. Okay, so, and I know my value should be somewhere between 0 and 1. That's my mental check to know that I've done it right. All right, so I got 0.509 on the top. Store that. Got 0.0166.
What'd you get on the bottom? Just sure.
So all of that, I got it as 30.74. Look at that. All right, if it asks for the percent, that would be 1.66% for the mole fraction for the sodium iodide. Gosh, I hope it's y'all's turn. So breaking my system to delete those clicker questions out because we are supposed to have a lot of clicker questions in here. Okay, I guess we'll just keep going. Did I go buy them?
Maybe you just got them confused as well. We click as what they were just. Because that's the most we've ever had.
Yeah, I'm just going back through them slowly. Yeah.
We can just do those on.
Somewhere I saved them in the wrong set of notes because you are supposed to have 3 clicker questions through the series and stuff. Yeah, but you don't have a clicker question. That's a bummer. Okay, maybe we'll get one in a second. Okay. I'm cheating you. Y'all don't want to be cheated your clicker questions. So colligative properties. What that means is properties that depend on the number of moles of particles, or the number of particles or moles of the solute are present. And the thing that makes it different is it doesn't matter what that solute is. Okay, it only matters on how much of it's present in the particular solution. And what it does is it causes a difference between the pure solvent and that solution that now contains the solute in it, and it makes the solution change because now you have different attractive forces between the solvent and solution and the solute because it's occupying part of the space where the intermolecular forces would have been just a pure solvent. And you're disrupting that balance that was there. And it changes some of the properties. In particular, we see things like the vapor pressure change. We'll see the boiling point change. We'll work problems with that and the freezing point change. Okay? So we use this type of a characteristic in something like antifreeze. So it's the time of year where you need to be aware of antifreeze in your car because what temperatures last night? Well below 0. If you just have water in your radiator and in your engine, because of the property of water, what happens to water when it freezes? Expands. If water is inside of the motor block in your car and it gets down to 15 degrees, like it did last night, or close to 20, you bought a new motor. Because as it expands, there's no place for that water to go. It'll actually break open a cast iron block or aluminum block. Okay? So to prevent that, you have to add something to the water in your car. You add antifreeze to it. What it does is lowers the freezing point. So the antifreeze inside of your motor doesn't freeze until you get to very, very low temperatures. And in Oklahoma, typically they tell us to run something like a 2 parts water, 1 part antifreeze. If you're going to go further north, you makes it 1 to 1. And the antifreeze that we typically use is a compound called ethylene glycol. Okay, ethylene glycol. I don't know if you remember, we talked about it in Gen Chem 1. It's one of the bad things because it gets in the glycolysis cycle. If your car has a leak in your coolant system, it drips antifreeze out. We usually see it in the a marker. Most antifreeze has a fluorescent dye in it that glows kind of green. You look at it, yellow or green. But the problem with it is that it has a sweet taste to it, and pets love it. See? So you're a cat lover, your antifreeze is leaking and stripping antifreeze, your cat goes and licks up the antifreeze, it gets in the glycolysis pathway and will kill your animal. And it just needs a couple of meals of it. And if you suspect your animal has been poisoned by antifreeze, you have to get your cat drunk. Literally, if you take them to the vet, they're going to give them ethanol. They're going to give them Everclear. That's what they do too, because it will make it eject that particular compound out. But one of the things that there was something on the news the other day about somewhere in around Carver area, or saw on Facebook, somebody had poisoned like 20 pets. They were doing something, killing all the pets in this neighborhood. Somebody got chased by a dog, or somebody got bit by a dog, so they decided they're wiping out everybody's dog. A common thing that people do is they'll take a piece of bread and they'll soak some antifreeze in it, throw it at the dog. Sweet tasting, dog eats it up, and in a matter of hours, the dog's dead. So, if you've got antifreeze dripping in your car, take home messages. Don't park it any place your pets can do it. Another thing I'll tell you, just for the sake of car ownership, as you're learning things in life, when you have somebody change your oil, if you don't change it yourself, make sure that they check the antifreeze. It takes them a matter of seconds to stick a little probe in there. They'll see how the balls float up. They measure the density of it, and they can tell you what temperature you're good for. Okay. So the first solvent, or the characteristic we're going to look at, is how vapor pressure changes. So if we take a pure solvent, what happens is there's a dynamic equilibrium that establishes between the liquid that's in the solution and the vapor pressure. So this is a sealed top on top of it. Sealed up. Can't see a loop. Okay. And there's going to be a equilibrium that's reached that produces a certain amount of pressure in the headspace. So the solvent reaches this vapor pressure, but what happens when we add a solute to it? As the solute starts to appear on the surface, the solute now occupies some of the spaces on the surface, and it causes the vapor pressure to change. Now there's not as many solvent molecules that can go out into the solution, so the result is a reduction in the rate of vaporization by the presence of the solute being present, and it causes a decrease in the amount of vapor pressure that's there. So the result of the solute is a decreased vapor pressure. How much of the solute's there is going to tell you how much your vapor pressure is going to go down. All right. Eventually, it's going to reach equilibrium again, but now it's just going to have a lower pressure as the result of fewer molecules being in this space above the liquid. Okay, so we use the term thirsty solutions. I'm the thirsty person today. Can't get enough to drink. So what happens if you take a concentrated solution and put it next to a dilute solution? What happens is it will draw the solvent from one side to the other. Right? In a similar way is that the concentrated solution draws the solvent that can go in the vapor phase from one side to the other. And the result is a reduction in vapor pressure. So here's the way that you set this experiment up. You take some type of a sealed container, so a bell jar works well, and you can put a beaker of water in one side. All right, so lost my drinks hit. So on one side, I'm going to put some water, pure water, and on the other side, I'm going to put some salt. So I'm going to put a solution that's got a fair amount of salt in it, like 3 molar sodium chloride. Now, these solutions want to be the same. And that's what happens when things try to reach equilibrium. We talked about if you had a diffusion barrier and you pull it out, the solutions would spread so that it's the same concentration all over. All right? Even though these two solutions are physically separated, the fact that they share a common vapor space, the vapor molecules can go out here and together. The thirsty solution is the salt solution. So what happens is that the molecules that are present from the water get transferred and absorbed in this, trying to reduce the concentration. They lower the concentration of the salt. So I could start with 100 mils in each one, come back the next day and look at it, and this one may be down to 20 mils. And the thirsty solution went up to 180 because it's trying to reduce the concentration. Okay? They're trying to get the vapor pressures to equalize out between the two solutions. Okay, so a way that we can measure the extent of this is Rayleigh's law. So what it does is it looks at the vapor pressure as a function of the mole fraction of how much solvent's pressure is present. So in this, the normal vapor pressure we describe as P naught. And it's going to be multiplied by the mole fraction representing the mole fraction of the solvent that's present. So if it's 100% solvent, mole fraction 1, the vapor pressure of the solvent is the vapor pressure. But when we start to add the solute to it, what that means is that number is always going to be less than 1, because as we add solute, we know that the vapor pressure of the solvent has to go down. It decreases as the amount of solute increases. Okay? And what happens is it continuously starts to decrease this vapor pressure. And if we look at the vapor pressures and how they, purple, the vapor pressures in the solution are always going to be lower than that of the pure solvent itself. So it causes reductions in vapor pressure. And it's directly proportional to the amount of the solvent that we have in that solution. So if we want to look at how much the vapor pressure has changed, we call it the vapor pressure lowering. The change in vapor pressure is equal to the vapor pressure of the pure solvent less the vapor pressure of the solution. So that's simply equal to the mole fraction of the solute times the vapor pressure of the solvent. Okay, and that's the key thing. This is solute. This is the minor component. And this is the solvent. This represents the major component we have in a solution. Okay, now so we know that the pieces have to equal the whole. And if our solute is non-volatile, it can evaporate. So if it's something like the sodium chloride, it's stuck there on one side. But if it's something that can evaporate, then both things that can go into the vapor phase, and it makes things a little bit more complex. So the total vapor pressure now, if it's a volatile solvent or solute, is that it's a combination of the pieces. So it's the total pressure that's observed is going to be the vapor pressure that comes from the solute plus the vapor pressure that comes from the solvent. But we still can use this Rayleigh's law to each one of those individually. So the vapor pressure of the solute is equal to its mole fraction times its vapor pressure, normal vapor pressure. That for the solvent is its mole fraction times its normal vapor pressure. And we can add those two things together to find the whole. So this gives us a way that we can look at thirsty solutions and we can understand these interactions and the extent between the two. Okay, so I hate this. You get a point for just being here, 100%. Okay. All right, here we go. Put them in, we're done. Okay? See you tomorrow. We'll work problems. There's, looks like 15 slides left to go over.
Okay.